Hello, everyone. So before we jump into the excitement of section 1.4, I want to briefly just sort of rehash what we've done in sections 1.1 through 1.3, because in a lot of ways, we kind of just kept answering the same question in those three sections, which was often, how do we solve a system of equations? How can we represent a system of equations? And what do the different solutions mean? So here we've got a system of equations, maybe the most straightforward way of representing this system, where we just list out each equation with each variable. So remember in section 1.1, I believe it was, we introduced something called the augmented matrix, which sort of just assigned a column to each variable and then one column for the right-hand side of the equals signs, and then just sort of put everything lined up in the matrix. So again, you can imagine kind of just putting this matrix on top of the system of equations and having all of the numbers match up. Remember then in section 1.2, we went over an algorithm that actually showed us how to use row reduction techniques to reduce this matrix to another matrix that allowed us to solve the system. Then in section 1.3, we showed that we can actually express this system of equations as a vector equation, where we sort of just take each of the columns of this matrix or take each of the coefficients attached to each variable, and we can write this equation out as a vector equation. And so each one of these representations of a system of equations has its uses depending on what context you were in and what you were wanting to talk about. Remember with vectors, it was helpful to talk about the span of a set of vectors and linear combinations of vectors, as we will see. But of course, sometimes it's useful to just look at the sort of equations as they are laid out. So in this section, we're going to introduce yet a new way to represent a system of equations and talk about some properties and then solve some more equations by row reducing. So first thing I want to do, we've got this definition if A is an m by n matrix with columns A1 through AN. And so remember, I think it was last section we introduced how we can represent sort of a matrix by its columns. And so this is basically how we are defining A here. And we let x be this vector x1 through xn. So x is a vector. Each of these x sub 1, x sub 2, up through x sub n are, sometimes they will represent variables, sometimes they will represent numbers. These are just individual entries in this vector x. And so this is just a vector in Rn. We'll define something called the matrix vector product, A times x, which you can think of as here A times x. This is the matrix A represented with this sort of column representation that we introduced. This is the vector x. And I'll show you how it works more definitively with a matrix, but this is in fact equal to the sum x1 times a1, where a1 is the column of the matrix, plus x2 times a2, so second column times second variable, all the way up through xn times an. So why is this useful? Well, notice we can take this system of equations, or specifically the right-hand side of this system of equations, ignoring the 3, 2, 1 for now, and write out, well, if we let this be my matrix A, so we'll let this be A, and let's say x is equal to the following vector, just x1, x2, x3. Well, so here's A, column 1, column 2, column 3. So this is my vector A1, my vector A2, my vector A3. Then what this definition tells me is that A times x is actually just equal to this vector equation I represented up here, 1, 4, 1 times x1 plus 2, 0, 1 times x2 plus 0, negative 3, 1 times x3. So all that A times x is this sort of matrix vector equation in this context of x being this vector of variables corresponding to a system of equations is just sort of a more compact way of representing what's going on, right? So I've got the augmented matrix, which I might have to write out. But if I were to take this matrix and say, well, A times x is equal to this, I've sort of got this more compact way of representing a system of equations. So matrix vector product, what you do, you take each column of the matrix, you multiply it by the corresponding indexed entry of the vector, and then you sum all of those vectors together. So in video 2, or the next video in this section, we'll actually go a little more into depth on how to take this matrix vector product and relate it to solutions of linear systems. All I want to do in this video is look at a few examples of this and sort of practice calculating these matrix vector products. I think it's a little weird at first to do so, but eventually it gets fairly intuitive. So let's say we wanted to do this with just a standard matrix and a vector, and let's say we didn't actually even have variables. Let's say I just wanted to calculate the product of the matrix 4, 1, 0, 2, 6, 1 times the vector 1, 2. So generally the way I'll do this is to use sort of I call it like the matrix multiplication dance, and eventually we'll start multiplying matrices together and we'll go over it again. But what you do is you take row, match it up with a vector, row, match it up with a vector, row, match it up with vector. And so what this means, if I want to calculate what this matrix vector product is equal to, I'm going to take the top row of my matrix, which is negative 4, 2, match it up with the vector, which is 1, 2, and so the first entry in the right-hand side of this equation will be negative 4 times 1 plus 2 times 2. So what I've done is I've taken these two entries, flipped it around clockwise, multiplied the corresponding matching entries, and then summed those entries. So 1, 6 matches up with 1, 2 to give me 1 times 1 plus 6 times 2. And then 0, 1 matches up with 1, 2 to give me 0 times 1 plus 1 times 2. Expanding all of this out, I think I got 0, 13, 2 for this product. So alternatively, if you would have preferred to sort of just follow the strict definition here, this is equal to 1 times the vector negative 4, 1, 0 plus 2 times the vector 2, 6, 1. And so notice this way of doing it is a little bit of a shorthand way, but kind of a quick way to calculate. This way is the official definition, and you can see that they do in fact agree. So some things to note about what's going on here that's a little easier to see with this definitive example. So notice that A is a what by what matrix. So it's got 3 rows and 2 columns. So A is a 3 by 2 matrix. Now, by definition, X has to be an Rn. So here notice A is an m by n matrix. So X has to be a vector of length equal to the number of columns in A. All right, so here A has 2 columns. So here this vector has to be an R2, right? But notice that the vector we get, that is this vector A times X, well, this vector has 3 entries, and so this vector lives in R3. And so in particular, notice that under this definition, the product A times X So here, again, we're assuming A is an m by n matrix and x is an Rn. A times x is a vector in Rm. So I'm multiplying my m by n 3 by 2 matrix times a vector of length 2 and getting a vector of length 3. And that will always be the case for any pair of indices m and n I pick for my matrix. And notice if the x is not a vector in Rn, that is if the length of x does not match up with the number of columns in A, then the product doesn't even work. So for example, if you were asked to calculate the product, well, actually we'll just call this a bad example because this is an incorrect product. Let's say I asked to calculate the following product, 4, 1, 0, 2, 6, 1 times 1, 2, 3. Well, this is impossible. Because, notice the number of columns in A is equal to 2, the length of this vector is 3. The dance won't work because when I try to match up negative 4, 2 with the vector, there's too many entries in the vector. All right, so there's a couple interesting properties that go along with this, kind of similar to what we did with our vector and scalar multiplication, vector addition and scalar multiplication rules that are worth going over. So I actually just want to finish up this video by going through a few more examples and a few properties that we get with this matrix vector multiplication that will come in handy again later. Again, I actually think both of these properties are fairly straightforward. I think it's a little less intuitive maybe than maybe the vector properties we went over before, but I think both of these are like properties that you would want to hold for these types of operations. So what property 1 says is that if I take, oh, no, that should be a v. If I take two vectors u plus v, then I can distribute A across their sum. Right, so A times quantity uv is equal to AU times AV. And just for the fun of it, I thought with this we could actually look at a concrete example. Since again, I think this is a little less intuitive right off the bat. So we'll let A be the matrix 1, 2, 3, 4. We'll let U be the vector 1, 2. And we'll let V be the vector 3, 4. Just for some odd symmetry. All right, so we want to show that A times UV is equal to A times U plus A times V. So notice here U plus V. Well, I just add component-wise across. So this is equal to 4, 6. All right, so A times U plus V is equal to 1, 2, 3, 4 times 4, 6. Now I'm going to do my matrix vector dance. So row 1, vector, I get 4 times 1 plus 2 times 6. Row 2, vector, I get 12 plus 24. And so this is equal to 1636. All right, now we'll do A times U. Again, top row matched up with vector is 1 times 1 plus 2 times 2 is 1 plus 4. 3 times 4 matched up with the vector, 3 plus 8. So this is equal to the vector 5, 11. And one more vector left to compute, A times V. All right, 1, 2 matched up with 3, 4 is equal to 11. 3, 4 matched up with 3, 4 is 9 times 9 plus 16, which is 25. And so notice a times b plus a times u does in fact equal a times u plus v. So it sort of, when you think about how all of the multiplication works, I think it makes sense to me that this should distribute. But it's always nice to see sort of an example confirming that it does. All right, so that's property 1. Property number 2, I think, is a little more straightforward. So property number 2 is that for any scalar c, a times c times u is equal to c times a u. And so all this is saying is that if I've got some scalar c multiplied by my vector u, I can factor that scalar out of the matrix vector equation and either do this in any order I want. So to see this, suppose c was equal to 2. Well, I know that 2 times vector u is equal to 4, not 4, 2, is equal to the vector 2, 4, right? And remember, that's just because to multiply a scalar times a vector, I just multiply the scalar times every entry in the vector. And so we'll do one more fun matrix vector multiplication. 1, 2, 3, 4 times 2, 4 is equal to 1, 2 matched up with 2, 4. I get 2 plus 8. 3, 4 matched up with 2, 4. I get 6 plus 16. Sure enough, that's equal to 10, 12. Nope, 10, 22, excuse me. Which notice is equal to 2 times 5, 11. And if you remember from up here, 5, 11 was the original product a times b. So, good thing to keep in mind when we're working with matrix vector products and matrix vector equations. We can call on these two properties whenever we want, of course, assuming that all of the correct dimensions for the matrix and the vectors line up. So, like I said, in video number 2, we will look at how we can apply this sort of new way of expressing an equation to actually solving linear equations and how it sort of fits into what we've been doing so far.